everyone. Today we're going to start with section 1.1, which is approximating areas. The goal of this section is I wanted to find a technique to find the area between a certain curve of my function f of x, my x-axis, on a certain interval a and b. We're going to approximate this area by finding shapes that we know the area of. So for example, a rectangle, I know that the area of a rectangle is just length times width. So I'm going to use this shape to approximate the area under the curve. We're going to talk more about it in details, but first, let's start with some notation, which is the sigma notation or the summation. So this letter is a Greek letter called sigma. We use it to express long terms of values in a compact way. This is going to be very helpful throughout the course, so let's start with it. So for example, if I want to add all integers from 1 to 10, so if I want to do that, I would just write 1 plus 2 up to 10, just add it up. And I can express it in an easier way where I can just skip a few terms. I'll do 1 plus 2 up to 10. Now using the sigma notation, we can get an even better notation where I can express this sum as the summation of a certain value I, where I goes from 1 up to 10. So this notation means that I'm adding my numbers from 1 to 10, which is way more compact than just writing numbers added up. Now in general, my sigma notation would look something like this. It's going to be the summation of ai, where I begins from 1 up to n. Here ai describes my terms. So for example here, my terms were just the integers from 1 to 10. In general, I express these terms in terms of ai, and I is called my index. So whenever you get a notation of this summation, it means that I'm evaluating each term, then summing up the values, starting with the value I equals 1 and ending with the value I equals n. So for example, if I have the summation where I begins from 3 up to 6 for certain terms ai, this is interpreted as a3 plus a4 plus a5 plus a6. So I'm evaluating each term for a certain value I, and then I'm adding all terms up. Similarly, if I have the summation of sj, where j goes from 1 to 5, I'm evaluating each term at each index, and then I'm adding them up. So this is s1 plus s2 plus s3, s4, and s5. So it's just a notation. Now we can use different letters. Like you saw here, I used s, I used j. The most common letters for indexes are I, J, K, M, N. That's just like the letters normally used in mathematics. Okay, so now let's see, why is this notation helpful? So if I want to write a sigma notation and evaluate the terms 7 to the I, where I goes from 1 to 3. So to solve it, first let's write the sigma notation of that. So here I'm adding up the terms 7 to the I, where I goes from 1 to 3, which means now I want to evaluate each term for each index. I'll start with 7 to the 1, then I add 7 to the 2 plus 7 to the 3. And now when you evaluate all of that, you're just going to get 7 plus 49 plus 343, and you just add them up. Similarly, for the second example here, if I want to write the sum in terms of sigma notation, I want to notice a pattern here. Now, if you look at the numerator, it's all 1. So that does not matter. So in my sum, my numerator is always 1. Now let's notice a pattern in the denominator. I'm going 2, 4, 8, 16, 32. If you think about it, these are just multiples of 2, which means if I start with I equals 1, 2 to the I, once you plug in the value 1 here, you're going to get the first term, which is 1/2. Now let's try I equals 2. Once you plug in I equals 2 here, you're going to get 1 over 2 to the 2, which is 1 over 4, which is my second term here. So where do we stop? If you look at the last term here, I got 1 over 32. And I know that 2 to the 5th is 32, which means I need to stop my summation at 5. Okay, so that's the general notation for the sum. It's just a way that we use, something that we use to describe certain terms added up. We have some important properties of the sigma notation. So if we assume that we have certain terms, A's and B terms, and we have C to be a constant, which is any number, and N and M are just positive integers. We have the summation of a constant where I goes from 1 to N. It's just N times C. Let's see why that works. For example, if I take the summation of 2 where I goes from 1 up to 3, this means I want to add 2 to itself 3 times. So this is just 2 times 3. So this is where we get N times C, because here my N is just 3. Similarly, if I have a C times certain terms, I can just take the C out and evaluate the summation with these terms by itself and then just multiply by your C. Now, if we have a sum inside of my summation, I can just distribute it. If I have a subtraction, I can also distribute it. And lastly, if I have a sum where I start with I equals 1 up to N, I can just split it. I'll have M, which is less than N. I'll split it into a summation from 1 up to N, M, and then the summation from M plus 1 up to N. So these are very helpful properties that we're going to use throughout the semester. Okay, so proofs of 2 and 3 are in the book. You can just read them through. They're not too difficult. Let's try and prove number 5 together. So here, the summation of AI from I equals 1 up to N. If we evaluate each term, I'm just plugging in the values of I, which is my index. A equals 1, 2, 3, up to N. Now, if you think about it, there's a hidden term AM between all of these terms. So I can write it as plus AM plus 1 up to AN. Now, I can combine these terms into one sum using the sigma notation, and I can combine these also using the sigma notation. But here my index starts at M plus 1 and it ends at N, which proves formula number 5. Okay, now since adding a bunch of terms, especially when your n is large, could be a bit difficult sometimes, there are some rules that could help us solve this problem. So if I'm adding up I, where I goes from 1 up to n, I can easily find the sum using this rule. I just find my n and plug it into this formula. Similarly, if I'm adding up I squared, I can find the sum directly using this formula. And similarly for I cubed, we have this formula. So the only thing that you need to do here is to determine your n, and once you have your n, you just substitute it in the formula and you get your sum directly. So let's see how this is useful. For example, if I want to find the sum of 5 times I plus 1 for I equals 1 up to 100. Now obviously, if I want to add all of these terms, it's going to take a long time because I have 100 terms. So what we do here is I want to use my properties and one of the rules to find this sum directly. So first of all, using property number 1.2, I can easily take the constant out of my sum. Next, using property 1.3, I can distribute this sum and now I can use distribution property to distribute the 5 over these sums. And using properties again and the rule, using the rule number 1, n here is equal to 100. So if you go to rule number 1, you know that the summation is just n times n plus 1 over 2. Using n equals 100, this is just 100 times this over 2 plus 5 times 100 using property number 1.1. And you can easily calculate this using a calculator, which is not recommended, so just try and practice solving these numbers by yourself since you're not allowed to have a calculator in the exam. Okay, so for the second example, I'll also use the properties where I can distribute the sum when I have a subtraction, and using the rules with n equals 5, this is just n plus 1, 2 times n plus 1 with n equals 5 divided by 6 minus, and you can evaluate it easily. So these are just using the rules. Similarly here, I can just distribute the sum, take the constant out, using the third rule for I cubed with n equals 15, this is just 15 squared, 15 plus 1 all squared divided by 4 minus 5 times 15 times 1 using the properties, and you can calculate it easily. Okay, so these are the general properties for the sigma notation. Now we're going to start the second topic of this section, which is approximating an area. So we're going to start with a continuous function f that's non-negative on a closed interval AB. Our goal here is I want to approximate the area bounded by f of x, x-axis, and the lines x equals a, x equals b. So if you look at the graph here, I have the graph of f of x, which is this curve, and I want to approximate the area under this curve, which is all of this. So the area that I want to find is the area between the curve, the x-axis, and the line x equals a and x equals b. So how do we approximate this? So to approximate it, I'm going to divide this area into small shapes with known area formulas. Usually, or like what we're going to use here is we're going to use rectangles because, like I said before, rectangles have the area of length times width, which I can easily find. Once we have, like for example, let's say I'm going to divide this area into these rectangles. Once I find the area for each one of these rectangles, the area under the whole curve is just adding these areas of rectangles, and we have an estimate of that area. Not quite equal to it, just approximation for it. Okay, so in general, if I have the interval AB, I want to divide this interval into n subintervals with equal width. So this width is going to be b minus a over n. So b, a are the points in the interval, and n is the number of rectangles that we're going to divide the area for. Okay, so we have this notation. Delta x is equal b minus a over n, which is my width. We're going to select points that are spaced equally, and x of 0 is always my a, x of n is always my b. And the difference between any 2 points that are consecutive is just b minus a over n. And to find x of I, we can use this formula. Okay, so these are just like a bunch of definitions. Let's see how we're going to use them to find or approximate the area. Before we start, let's state some definition here. If we divide the interval AB into subintervals, we're going to have x of 0, x1, this is my first interval, x1, x2, my second interval, up to xn minus 1, xn, that's the last interval. We called each single one of these intervals a partition of a and b. If all of these intervals have the same width, which means that x0, x1 has a certain width, x1, x2 have the same width as x0, x1, xn minus 1 and xn also have the same width. When we have that, we call it a regular partition. We're going to use a regular partition to estimate an area under the curve. Okay, so we have two main methods to do that. We have the left endpoint approximation and we have the right endpoint approximation. To find the area A under the curve f on the interval, we're gonna divide our interval into subintervals like we did before. Then we're gonna construct a rectangle with width delta x and height equals f of xi minus 1. So since we said that the area of a rectangle is just length times width, here our length is just the height and the width is just delta x. So if I want to find the area for each single rectangle that I constructed, the area is just going to be the multiplication of fx minus 1 times delta x. And if we add up all of these areas, we're going to get an approximation value for the area under the curve. So obviously it's just a bunch of definitions for now. It doesn't make a lot of sense, right? So let's look at the graph first. If I have a curve of f of x here, if I divide the area under the curve into these rectangles, and only using the left endpoints for each rectangle, I can easily find the area under the curve by finding the area of each single rectangle and then adding up all of these areas. So let's do an example for it to make more sense. Okay, so if I want to use the lift endpoint approximation to approximate the area under a curve f of x equals x squared on an interval from 0 to 6, dividing it into 3 rectangles and then dividing it into 6 rectangles. Okay, so let's start by graphing x squared on my interval. So from 0 to 6, this is the graph of x squared, where 0 is my A, 6 is my B. The first step of evaluating the area is I want to find delta x, which is B minus A over N. So this is just 6 minus 0, and for the case where N equals 3, I'm just going to divide by 3. So this is 2. So now what you do is I'm going to start with my x of 0, which is 0, and then we're just adding the width, delta x, until we reach my x of n. So 0 plus 2, that's 2, and then 2 plus 2, that's 4, 4 plus 2, that's 6, so we're done dividing. Now what we do, since it's a left endpoint approximation, I'm gonna graph vertical lines of the endpoints, of the left endpoints. So here at x equals 0, the vertical line is just a point. For 2, if I graph a vertical line until I reach the curve, that's going to be my line. And then lastly, for 4, that's going to be my line. After you do that, you just create rectangles. Okay, so now for the first rectangle here, I don't have an area. So the area for the first rectangle is just 0. Now the area for the second rectangle, I know that the area of a rectangle is just width times height. So here the width is 4 minus 2, which is 2. Now my height here, we're going to find it using f of either 2 or 4. But since we're doing a left endpoint approximation, we're going to take f of 2. So this is my height. At this point here, I have the point 2, f of 2. So that's why f of 2 is my height, because it's my y value. So the area for this rectangle is just 2 times f of 2. So this is 2 times 2 squared, since f of x is just x squared, and that's 8. Repeating the same process for this rectangle, we have the width of 2, the length of f of 4. So the area of this rectangle is just 2 times f of 4, which is 2 times 4 squared, and so on. So this is how you approximate an area under the curve using rectangles. Because I already know the areas, I just find the area for each rectangle separately and just add them up. So the area in general, it's going to be 0 plus 8 plus 32. And just, so the area is almost 40. So if we go back here, the area using a left endpoint approximation, you just find the height of the left endpoints, you multiply it by the width, which is equal, since we're doing a regular partition, we're dividing the area into equal length, equal widths, so it's always going to be delta x. So now using the sigma notation, I can write it in a compact way using the summation notation, where I'm going to have f of x I minus 1 times delta x. And that's how we approximate the area using a left endpoint approximation. So let's try the second example just to make sure that we understand it. Similarly here, we have the curve of f of x equals x squared from 0 to 6. But here, instead of having n equals to be 3, my n is 6. So when you find the widths, this is just 6 minus 0 over 6, which is 1. So I'm going to start with x of 0 equals to 0, and then I'm going to add 1 to that. So that's 1, 2, 3, 4, and 5, and 6. So we stop here. Since we were doing an endpoint, a left endpoint, we're going to go at the end, at the left endpoints, and graph vertical lines until we reach the graph for each one of them. And then we're just gonna connect them to create rectangles. And then to find the area, this is just L of 6, which is the summation of f x minus 1 times delta x, which is just 1, I equals to 1, and this is my n, so up to 6. So this is just f of 0 times 1 plus all of these. Where each term here, each term represents the area of one of these rectangles. Once you evaluate it, since f of x here is x squared, you just substitute, so 0 plus 1, and you just add them up. Which is equal to 55. Okay, I'm going to state a fact here that I'll show you an example about. The more rectangles you use, the better the estimation is going to be. So keep that in mind, and I'll show you an example in a bit. Okay, so the second method here is using the right endpoint approximation. Repeating the same exact process, but instead of taking the height to be f of x minus 1, which is the left endpoint, I'm going to take my height to be f of xi using the right endpoints. So the right endpoints are these. So here we include x of n. In the left endpoint, we exclude x of n, and I take x of 0. Here I exclude x of 0, and I take x of n. Using the same method as the left endpoint, we can approximate a right endpoint. So let's try the same example. If I have x squared on the interval from 0 to 6, my n is 3, so my widths are going to be 6 minus 0 over 3, so that's just 2. We start at x equals 0, which is 0 here, and just add to these points until you get your x of n. So now, since we're doing a right endpoint approximation, I use my right endpoints and I draw vertical lines until I reach the curve, and then I just connect them to create rectangles. To find the area under the curve using the right endpoint approximation. Similarly, I just find the area for each rectangle separately, add them up, and that would approximate my area. So here, the area for this rectangle, for example, the width is 2, where the height here, since I'm using an endpoint, is f of 2. So the area would be 2 times f of 2. Similarly here, the width is 2. And the height here is f of 4. And for the last rectangle, doing the same thing. 2 times f of 6, because here my height is 6. Is at 6, so my point here is f of 6, which is my y value, so you can easily find it. So the area is 2 times 2 squared plus 2 times 4 squared, 2 times 6 squared, and so on. So if you go back here, you can see that the area using the right endpoint can be approximated by finding the area for each rectangle separately, then adding them up. If I want to write it as a sigma notation here, the only difference is I'm taking f of xi, not x minus 1. Not xi minus 1, sorry, like we did at the left endpoint. Okay, so just to summarize, when I'm approximating an area, I'm just approximating it using the areas for rectangles, either with left endpoints or right endpoints. Okay, so when we use a small number of interval, neither the left endpoint or the right endpoints give an accurate estimation. So to get a more accurate estimation, like I said before, we can take more rectangles to create a more accurate approximation. So let's look at the example in the book. So here we have the function x minus 1 cubed plus 4, and I want to use the left endpoint approximation with n equals 4. The first step is I want to find my width, which is b minus a over 4. Since the interval used is from 0 to 2, I just do minus 0 over 4, which is 1/2. So I'm dividing up my interval using width half. So if you look at the graph here, I'm dividing up my area into 4 rectangles. Since it's a left endpoint approximation, I'm going to take these points. So if you look here, I'm taking 0, then adding 1/2, then adding another 1/2, which is 1, another 1/2, which is 1.5, and I'm multiplying by my delta x. If you add them up, you should get an approximation for the area under the curve here. Now what happens if I divide the interval into 8 rectangles? If you do that, your delta x, which is my width, is going to be 1/4, which is 0.25. I'm going to start with 0 since I'm doing a left endpoint approximation, and I'll keep adding 0.25 here and multiplying by the width to create the area of all of these rectangles. Once you add them up, you should get an approximation for the area under the curve. And if you notice here, I got a slightly different number. Okay, what happens if I divide it even more? What if I have n equals 32? So I have a 32 rectangles. If I do that, you can find your delta x to be equal to this. sorry for that. Yeah, so I always start with 0 since I'm doing a left endpoint approximation, and I keep adding delta x to my 0 until I get to here, and I multiply each f of that number by your delta x, which is the same for each one of them, to get the area for each rectangle separately, and then we add them up, so we get a more accurate approximation. Okay, so doing the same exact process but with a right endpoint approximation, you can see here that I already know when n is 4, my delta x is 1/2. But here, since I'm doing a right endpoint approximation, we're gonna start with 1/2 and reach x of n, which is 2. If you add them up, you get 8.5. And similarly, if I take a right endpoint approximation with n equals to 8, we're going to do the same exact process, and we're going to get 8.25. And similarly, doing it for 32, we got this number. So let's see what that means. If you look at the table here, the difference in the area with left endpoints and right endpoints is quite big. It's 1. But when we increase the number of rectangles we're taking, the areas got closer to each other. And the more we increase it, the closer the areas of the left and right endpoints are going to be, which means I'm getting a more accurate estimation for my area. So that's why the more you increase your n, the more accurate your estimation is going to be. Okay, so now as an exercise, try estimation the area with n equals 5 for this example. Okay, so now let's start the last topic that we're going to go over today, which is Riemann sums. So far we've been using left and right endpoints to find the height of the rectangle. But technically, we can use any point in the subinterval that we're getting. So here, if we choose any point in the subinterval, using the height f of xi star, we can easily approximate the area by taking the sum of the areas for each rectangle separately, which is the height times the width. Okay, so keeping that in mind, let's go over this definition. We have a function on a closed interval AB. We have a regular partition that we talked about earlier, and delta x is my width on a subinterval. If we take any point in my subinterval, I can define a Riemann sum to be the summation of f of xi star times delta x. So the reason why Riemann sums are important is because they give better approximation for larger values of n. So keeping that in mind, it means that I can find the area under the curve by finding the limit for the Riemann sum. By taking n to be very, very large, I can easily find the summation, the limit of the summation, and that would be my area. Okay, so let's go over some notes here. Since my function is continuous, my limit always exists here, and it's unique. Take it as a fact. It can be proven, but it's very difficult for Calc 2, so just keep that in mind. Okay, so although any choice of x star gives an estimation of the area under the curve, we don't know whether this estimate is too high or too low. But we can choose xi to either overestimate or underestimate. So what does that mean? When we overestimate, let's call it an upper sum, we're going to choose xi such that f of xi star is going to be my maximum on that subinterval that I'm dealing with. And if I do an underestimate, which is called the lower sum, once we pick my xi star, f of xi star is going to be a minimum function. Okay, so I'm going to do an example in a bit to make sure that you understand this more. But let's state this fact real quick. If my function is either increasing or decreasing, then the maximum values are going to be my maximum and minimum values are going to be my endpoints, which means the upper and lower sum are going to go back to being a left and right endpoint approximation like we did before. So let's go over this example. I want to find the lower sum for my function x cubed minus 1 on the interval 2 to 4 when n is equal to 4. So a lower sum, it means I'm going to underestimate, so I'm taking a minimum. So let's graph this function on this interval and see if we can say anything about whether this function is increasing or decreasing. Okay, so if you graph this function, it's going to look something like this. Taking it on the interval from 2 to 4, we only care about this part. So on 2 to 4, my function is increasing. Since my function is increasing, the lower sum is going to be a left endpoint approximation. Okay, why is that, right? So let's look back here. We said the lower sum takes a minimum. And since function is increasing, the minimum is going to be always an endpoint to the left. So 2 is my minimum. Because my function is increasing, the values of f is only increasing when I'm going up to 4. So my minimum is 2, which means I'm going to take a left endpoint. So that's why I'm doing a left endpoint approximation. So since a left endpoint approximation, we're going to repeat the same process. I'm just going to find my delta x. So that's 4 minus 2, b minus a over my n, which is 4. So this is just 1/2. So I'm going to divide this area into 4 points by adding 1/2 to my x0, which is 2. So I'm just adding. And since we're doing a left endpoint approximation, I'm going to put vertical lines until I hit the graph off using the left endpoints, and then I'll just connect to create rectangles here. So I have these 4 rectangles that's going to approximate my area. So here the area using a left endpoint approximation is just the summation of f of x minus 1 times my delta x, which is 1/2, from I equals 1 to 4, because 4 is just my n. Now, since f of xi minus 1, since f is x cubed minus 1, this is just the summation of xi minus 1 cubed minus 1, all multiplied by 1/2, I equals to 1 up to 4. Once you substitute, you're going to get x of 0 cubed minus 1 half and so on. So here x of 0 is my 2, So this is 2 cubed minus 1 half, plus 2 and 1/2 cubed minus 1 1/2. And you just take the points by adding 1/2. And you add them up. So this represents the area for the first rectangle, then the second rectangle, this is the area of the third, and lastly, this is the area of the fourth. Once you calculate that, you add them up, and this is your approximation. So here, this is an approximation, so it's not completely the area, because you can see here, there are like some gaps. But for now, it's only approximation using the summation. In next lectures, we're going to talk about finding the area accurately using integration. Okay, so now let's do the second part. We have the graph, we want to take the graph of cosine on the interval from 0 to pi over 2, where n is equal to 5. So the first step is always, you want to graph. That's why it's important for you to know the graphs of like the main functions. So cosine on this interval looks like this. And we know that the highest value that cosine attains is just 1. Okay, so here, as you can notice, my function is decreasing. Now, since it's decreasing and I want to find an upper sum is an overestimation using the maximum of my function. So if you look at the graph here, my maximum is at this point, which is my x of 0 here, which is 0. So since I'm using, since my function is decreasing and I want to find an upper sum, which means I want to find the maximum, and the maximum is always to the left of the points, then the upper sum is also here a left endpoint approximation. Repeating the same process again, I just start by finding my width, which is b minus a, so b minus a over n. So you start with your x of 0 and you keep adding the width until you reach your x of n. So here 5 pi over 10 is just pi over 2. We're doing a left endpoint approximation, so you just take vertical lines off the endpoint to create your rectangles, and then you just connect to get the rectangles. So here, this is just going to be a 0, so I don't have a fifth rectangle. So my area is just f of 0 times the width, f of pi over 10 times the width, 2 pi over 10 times the width, and lastly, these times the width. And like I said, my last rectangle, obviously I can write it, but since f of pi over 2, which is cosine pi pi over 2 is just 0, this is just going to vanish into 0, so it doesn't matter. So here you can just calculate each one separately, which represents the area for each rectangle separately. You add them up and you approximate your area. So this is it for the first section, which is 1.1. If you have any questions, please feel free to email me. We can go over some of the concepts again if you want to. And now if you go to homework 1, you can do problem number 10. So I would recommend just watching the video, then doing the suggested problems from the homework, so it would be easier for you to submit it on time. Let me know if you have any questions, and good luck.